everyone. Welcome to lesson 3.1 part 2. Now we are going to take a look at the video from Dr. Dan Garcia, who explains about abstraction and generalization in a fun way. So let's take a look at this.
So the next big topic is abstraction. And abstraction is one of the most powerful ideas in all of computer science. It is the central idea in CS10. And abstraction is about two pieces. If you kind of say, well, what do you mean by abstraction? We typically think of two pieces. One is detail removal. It's about removing all the minutiae of the detail to focus on the essentials. It's also about generalization. So there are kind of two pieces of that, and there are definitions here on the slide. There are two pieces of what abstraction is, and the key is understanding how each of those is relevant. So let's look at detail removal first. So let's say you were thinking about a map to a wedding. Anybody have go to a wedding and have a really great detailed map of like hand-drawn, calligraphy drawn to the wedding? Anybody have seen one of these things I'm talking about? Nobody. All right. Well, this killed in the 70s. So in the 70s, we had a lot of these maps to places, maps to weddings. And what you would see is like a big picture of like train station or like airport. And then some lines, very simple, beautifully drawn lines, like artistically done, but kind of accurate. And then it'd be like big, important left turn here with a shell sign and, and a blinking cow going, ha, ha. And then they'd draw that in the map, but they wouldn't draw any other roads, right? And then they'd have, they'd draw like 15 miles and they'd say, okay, here's our house at the farm past that. This is how you get from the airport, the railway station to the wedding at the farm, okay? So think of Google Maps now. And think of what they do. If you say, I want a map from A to B, they print just the normal map. Maybe a zoomed in perfect map for that. But maybe that's way more information than you need. Maybe you only need the critical couple of lines, and maybe you want them to even zoom in more on the critical turn, right? The Google map isn't going to tell you that there's a critical turn here, or that's the only thing you need to worry about. It's a lot of information, right? Look at the picture on the left. That's a lot of information to understand how to get from A to B. The picture in the middle is the selected results. So I want to give credit for this image as well for this work to Manish Agarwala, who's a professor here in the computer science department, or in the ECS department, computer science division of our school. And he has done this thing, a piece of work called an automated generalization of detail maps. And the idea is they take normal Google Maps, and they have their own access to the Microsoft database as well, and they say, let me now make a simplification, and they come up with automated, this thing that used to take people, hours and days to hand draw. They come up with only the essential roads. So that is a perfect example of abstraction. You're abstracting away all the detail, all the roads and stuff, to only the roads you need. It's really beautiful and a great example. Another one about detail removal, and in CS10, is, let's say you're trying to write, say, a simulation. And you're trying to do a simulation of, traffic, say. And you say, okay, that means, how does traffic? Traffic is caused by people in cars. So do I start by going into the computer and modeling what a car looks like? No. Do I start by asking each person what they had for breakfast that day? No. How would you generalize people? Probably down to what you need for a traffic simulation. So the abstraction of a person in that model might be a single point, right? It's your center of mass and where you are in your car, or the center of mass of the car, say. And you can watch all these dots, and a visualization goes through, and you can measure traffic that way. What if we were doing a measurement of income, and how that compares to what school you went to, and how that compares to how much money the school got? Well, maybe when you generalize a person, you're no longer looking at a dot. You don't care about the XYZ coordinates. You care about what their income was, what their high school education was, whether they went to college. You care about more things about a person. So in one case, the traffic simulation, you only cared about their center of mass and XYZ coordinates. In the model of how income and education can contribute to local K-12 schools and success, you might be looking at more features of what a person has. But you'd be throwing away the XYZ position because you don't care about that in that simulation. Does that make sense? So you're thinking about different things. So the idea of this is focus on the essence. You're doing some simulation or some program. What do you need from that, from each particular piece of data, and throw the rest of it away to make your life simpler. In generalization, here's a model where you have a farm. I love this example. You have a farm and many different kinds of food. and you're going to leave your farm, and you have to give directions to the person who's going to be taking over as you're on vacation of how to feed these animals. And so you write a note. The first note says, to feed a dog, put the dog food in the dog dish. And then you have another note, and it says, to feed a chicken, put the chicken food in the chicken dish. And you have another animal, and you say, to feed a rabbit, put the rabbit food in the rabbit dish. And you start to get bored very quickly about this process. And you ask yourself, what would be a better way to do that? It's obvious. The answer is to feed animal, put the animal food in the animal dish. And that's obviously so simple you need to tell somebody, but that's a generalization where it works for any of those animals. I generalized a pattern. If you open the joy of cooking, you will not see to make a strawberry milkshake, you take milk and sugar and cream and strawberries. And the next page you won't see to make a raspberry milkshake, milk and cream and sugar and raspberries. Because what do they say? They say to make a milkshake, milk and cream and sugar and add fruit. You see that? They've done the same thing. They've realized that rather than have a copy of the same thing, a copy of the strawberry, a copy of the raspberry, a copy of the boysenberry, there's a generalization, add fruit here. And that's the generalization task. Isn't that cool? So, that's how you can do that better, obviously, and this is the answer here for that. So the point of that is important from us from a computer science point of view. One of the meta things, not on the slide, this might be a point to add extra notes because it's not on the slide, is one of the meta lessons you'll learn in computer science is you never want to have a copy. If you can, you have a single source of truth, as we mentioned before, how we're passing our information to the class. A single source of truth. So that means you never want to have a copy. You want to have to make a milkshake, and that's the only sheet you have. It doesn't make any sense to have us to make a strawberry, to make a raspberry, to make a boysenberry, because let's say you find a typo in the strawberry one, and you make a change in the strawberry one, but you forget to fix the typo in the raspberry and the boysenberry. So that means you've now have inconsistency, right? You didn't fix the typo all three places. That was crazy. So you want to have one single source of truth. And that's a new thing. Write that down. Single source of truth, important thing. Okay, not on the slides. As you're going to see that in CS10, we are going to be writing functions. And we'll have a whole lecture on what functions are, but it comes from math. It comes from the mathematical idea of a function. The sine function takes an input, which is an angle, and outputs a number. It's the sine of that angle. And you can think of a function, just like on the slides, as a machine. That's a function. Think of a function in general as a machine. There's one input, you turn the crank, and this output comes sine of that input. That idea of that input is your generalization. You see? Rather than writing something that says, well, this is a box that generates sine of 20, and this box generates sine of 50, and this box generates sine of 10, what you have is a sine box that takes an input. You have a make a milkshake box that takes an input. See how they're connected? So we'll see this in CS10, that we're going to be building functions, and how you decide to have a parameter to generalize that function to make it more powerful is great. If I see a student writing, let me draw a square, and then let me draw a triangle, and let me draw a pentagon, I would hope the student would think that's the same kind of thing. You should really be writing a let me draw an n-gon, where n could be 3, it makes a triangle. 4, it makes a square. 5, it makes a pentagon, etc. See that? That's a way of you thinking about, wait, why am I having 3 different copies of basically the same code? Let's generalize that and pull that out as an input, like sine had an input. Let's make an input to that draw, and now I have draw, which takes a number of angles, the number of sides, I'm saying. Okay? Good stuff. So, in summary, this is just a little bit of introduction to the most powerful idea in computing. Last lecture, I'm going to say, what was the biggest idea I saw over and over all class? You're going to say, abstraction, Dan, because abstraction really is the most important idea you're going to learn in this class. So, the other piece of it is, it's one of the big ideas of computational thinking. And what that means is, it's thinking like a computer scientist. The first thing that we all do inherently, without even thinking about it, is think abstractly. You give me a problem, I'm going to try to simplify it. You give me a problem, I'm going to try to generalize it so I don't have to have copies of the same thing. So all of us are doing this all the time. It becomes ingrained in your being. And so one of the things I hope you get in CS10 is this abstracting process will become natural to you as you do more and more of it. It's going to be really fun. Okay? So think about driving a car. Let's just one more example before we leave. Driving a car. How many of you know how a car totally works? Totally works down to the nuts and bolts, the grease, the pistons, the solenoids, the current. Nobody. Not a single person can explain to me like Car Talk could how a car works from the top all the way to the bottom. How many of you can drive? Hands up. Everybody, okay? So, unless you grew up in Manhattan, which is where I grew up near Manhattan, but many of my friends couldn't drive because you don't drive in Manhattan. So, why can you drive even though you don't know how something works? That's also abstraction. So there's another piece of abstraction which isn't generalization or detail removal, which is you don't need to know how something works to be able to use it effectively, which is like driving. Another piece of it is you can change what's behind the abstraction, how sign works, without telling the user. It's like that's a really powerful idea. And so here's an interesting idea. How many of you know that when you push on the brakes on a hybrid car, it's actually recharging the batteries? Maybe a couple of you. 5 years before that, it was a combination of hydraulics and mechanical. Before that, it was purely mechanical. And you had to be really strong to stop a big truck back in the early days. Honestly, the truck drivers back in the early days before hydraulics came in had to be the beefiest, strongest people, because when that truck was coming up and you got to brake it, you have to use all the power of your body to put the mechanical force to grab those wheels. And only when they added power assist brakes and power brakes could anybody of any size drive a truck, because it was only the mechanical linkage that was braking that truck. Okay? But guess what? Did you have to tell the user? I mean, aside from the truck example, obviously. But did you have to tell the user when today's technology recharges the batteries or has a hydraulic assist? No. It's the same interface. The left button, the left pedal is slow the car down, and the right pedal is accelerate, right? What do you call the right pedal, by the way? The gas pedal. People who own the Nissan Leaf, an electric car, purely electric, you know what they call their right pedal? The gas pedal. They are still using how it was done to label that. You're not allowed to do that. We call that an abstraction violation. Extra, write this down. Abstraction violation. Because what they've done is they've looked past the abstraction barrier of how it's done to say, oh, let's call it the gas pedal, because in the olden days it was only gas being added to the system. But nowadays it is add more energy of current to the electric motors. But they still call it a gas pedal. They shouldn't. It's the acceleration pedal, or it's the, go faster pedal if you want to kind of use the vernacular. So long story short, there's a couple of extra ideas. I had this last slide, which is, one is there's a barrier. You're not supposed to look beyond that barrier to how things work. You don't need to. You don't need to worry about it. I could change the brakes to make them do something else. When I push the brakes, it phones home. Dan's pushing the brakes. I don't need to tell you that, because it still does the job of braking the car. So I could change what's below when you push the button. What happens? Don't need to worry about it. Don't need to tell the user because of that abstraction barrier. That's that idea. And it was a violation to poke below and look at it. You're not supposed to do that. And people have done that in the use of learning that it's called a gas pedal. Because now when I change what it is, it's no longer relevant. It's a bug. So think of that when writing a program. We'll see this again. This will be just an intro. When we write a program, you're not supposed to look at how I write the program. If you're kind of using my helper routine, I did a helper routine to draw a square. You're not supposed to know how I did that. I could be drawing pixels. I could be drawing lines. I could be drawing a big box and then erasing the middle. I could be doing 10 different things. But you're not allowed to look at how I do that. Because if I change it, your code should still work. But if you happen to know what I do and then make use of it, then your code may break if I change what's below that line. Does that make sense? So that's a really important barrier called the abstraction barrier. That's an important thing too. All right. That's the end of the abstraction lecture, folks. I really hope you enjoy CS10. Welcome to the class. It's going to be an awesome year. Yeah! Woo! All right. It's a late day. All right.
Now that you have seen examples of abstraction and generalization, I'm going to show you a program that I wrote for my artificial intelligence class, which is also kind of an abstraction. So here's a problem. You're given a map like this in a text format. So it just says source and destination and what's the distance between those two. And as we saw from our previous video, these places are called nodes, and the edges are the distance. Edges represent the distance between two nodes. So the problem here is, if you feed the program any two places for example, Berlin or Munich, then you should be able to find the shortest route between these two places. So here's a program. This is a program you can do. You can even clone this from this Git repo and follow the instructions over here to run this program. I've already cloned it over here. And now I'm going to use map, and this is the input. And let's see, which two places do I want to find the distance between. So let's see, let's do BREMEN and MUNICH. So over here, this is an abstraction in the sense that I'm providing just the input text or this map in a textual format, and the two places that I want to find the shortest distance between, or a route between, and I just hit enter, and it should be able to generate it. You do not need to know how I'm doing this. So any other program can feed this information into this program and just get the output without knowing how it's calculating this distance. So let's take a look. After all these calculations, it's checking all the routes, and now we got one shortest route that is from Bremen to Hanover. We are going over here, and Hanover to Magdeburg, and from here to here, and here to here, and over here at Munich. And you can take a look at this map and see if this is really the shortest route. There are different algorithms that can be used to do this, so I can change the underlying information, and still the user wouldn't know what happened or how the route is being calculated. Now in our next video, we're going to take a look into building custom blocks and using the concept of abstraction and generalization to make our program better. So I'll see you in next video.